So good afternoon everyone, and thank you for your presence in this lazy afternoon. So it gives me pleasure to actually share with you the recent work that we have been doing in our group. Much of this is unpublished still. So I would like to talk about rotational synchronization of spiral and some scroll wave phenomena. So we work on chemical reaction diffusion processes. So this is a class of systems that has been introduced today in the earlier sessions, and we look at the spiral and scroll wave dynamics, and they are important, as we all know, because they occur in lot of biological processes and are used, and we need to understand the dynamics to understand what happens in the neuronal tissue and more so in the cardiac muscles, where they are responsible for the notorious ventricular fibrillation and cardiac arrest. So before I move into my research, I would like to welcome you all to come to the conference on oscillations and dynamic instabilities. Of course, it is chemical systems, but I think this is the only Gordon conference related to nonlinear dynamics, and we welcome everybody who works on pattern formation, active flow, synchronization networks, and self-organizing materials. So moving to our experiments at IIT Guwahati, we do our experiments in a Petri dish mostly, where we observe it from the top, and we store our information in the PC, which are later on analyzed. And this is one simple video of a spiral wave. This red dot has been put by us later on to show you that the tip of the spiral in the BZ medium actually rotates around a geometry which is circular in shape. So this can be defined to be the core of the spiral, and the core size depends on the recipe that we choose, the chemical recipe. For this case, it is 0.09 centimeter, and we can also determine the time period and the wavelength of the waves. For numerical simulation, we choose simple reaction diffusion system, and either it's the Barclay model, which is the simple mathematical model, or the more specific originator model is chosen. And depending again about the parameter space that we choose or the parameter values, we get particular values of the wavelength, the time period, and the core size. So first we will talk about the interaction of free spiral rotors. So this is something that people had looked at, but not a network of rotors so much. So what we did is we looked at, this is our numerical results first of all, when we keep a pair of spirals, they are counter rotating, one is clockwise, the other anti-clockwise. When they are far apart, then they keep on rotating around their circular trajectories. When we bring them close, they start repelling each other, and when we bring them even closer, they attract, and when they are very close, they annihilate. A plus and a minus charge annihilates each other. So we made a phase diagram out of the two rotor system, and what we found is there is a phase diagram shows a critical distance. This critical distance is where the no interaction of the two rotors moves into an interacting regime, and their repulsion changes to annihilation at half the critical distance, which was very interesting because the critical distance turned out to be the difference between the wavelength of the waves, the spiral wave arms, and the core distance. So basically, if one core is within the wavelength of the other, then they are in the interacting regime. Experimental results with our BZ showed exactly similar results, where we again found a critical distance which was equal to lambda minus ds. So then we actually moved to a network, or in this case 4 or 2 pairs of spirals, and we saw that depending on the distances, the horizontal and the vertical distances d and l, they could either attract and annihilate, they could repel, they could stay where they are if they are very far apart, or they could show this spontaneous symmetry breaking. So this was something which was very interesting and something not seen before. So this was something that actually brought in a lot of interest, and this phase diagram shows us this interesting area. We had this symmetry breaking, spontaneous symmetry breaking instability. So then we thought that can we consider the spirals as candidates for the study of synchronization, because whenever I come to the nonlinear dynamic conferences, everybody talks about synchronization and chimera, and we wanted to see that. But as you can see, the spirals, when they are near each other, they all run away in space. So how do we figure out what is their phase, what is their frequency, because they are meandering. So then we thought of the process of pinning. So pinning is a process which was known before. If you bring a spiral near a heterogeneity, so in our cases, they could be glass beads, or they could be rubber cylinders through which the wave cannot pass. So, they are inexcitable obstacles. So, the wave will stick there and it will rotate around it. So, here we can take that to pin them to specific sites. And another thing is, depending on the size, the diameter or the radius of these pinning obstacles, we can actually control frequencies or time periods. For example, a free spiral has a time period of 10 minutes in this particular geometry or recipe. With sizes of pin 1.8 millimeter, the time period becomes 12 minutes. 2.7 millimeters gives us 18 minutes time period, and 3.6 millimeter gives us 24 minutes time period. So, we can do two things. We control the speeds as well as we fix them at a point. So, let us see what happens. So, these are experimental results, and we begin with two identical heterogeneity to see what happens. And as you can see that the x, because they are counter rotating, the x, they go towards each other. So, the x is opposite each other, but the y, in the y coordinate they go up and down together. So, we basically focus in the y coordinate from now on just to see, and the phase diagram shows you that they are synchronized. This is same, they begin same, they remain same. Now, these are two obstacles of different diameter, 1.8 and 2.7. Initially they have different time periods, quite different as you can see, and the phase diagram is all over the place. But after about more than 2 hours, you see that they are in sync. Though there is a slight phase lag due to the difference in the size of the obstacles, but you can see that they have come to sync and the time periods are exactly same. These are numerical studies of a similar kind done in the Bakler model, and we can see that starting with different frequencies we come to exact sync here because they are quite close, the diameters. Now, what happens when the two are very different? I will show you one experiment just to show you how the experiment looks like. So, but you will not really understand much. There are two very interesting phenomena which we come across here. One is the phase resetting dynamics, and another is, I will just show you in the next one. Maybe this is something you can understand. During one rotation period, you can see we began with a plus and a minus, right, singularities. But there is a small window within one period where we end up with two pluses and two minuses. So, this is a bonus when one is very big and one is very small. You get this wave giving us two new singularities, and you can see that this plus and the minus, they approach each other, they annihilate there, and as if the minus tunnels suddenly here. So, this is the resetting. You are resetting the phase suddenly because these two will annihilate and this minus will take the space, again go there, annihilate, come back. So, this is an interesting dynamics which we saw. Here you can say they are completely anti in phase in the experiment where they are quite different. The time periods were initially one was 12, the other was 24, so almost double, yeah. And finally, the time periods have merged at 12 minutes. So, going to the numerical simulation of the same phenomena, you can see that here this phase resetting is very much visible here. You have an extra peak which shows you the extra singularities that have formed in this system. Then we try to vary the distances between the two rotors for a pair of such rotors, and we see that this distance linearly increases. So, the time required for synchronization linearly increases, which is understandable. So, it requires one rotor more time to attract or more time to basically talk to its neighbor. But when we look at this between these, like for a given distance, when you look about when they are comparable size, they take more time to synchronize than when one is much larger than the other. This was something very interesting again. So, we did some results, but these are 3D scroll waves from previous results. So, we had studied these kind of scroll waves which are 3-dimensional waves. When they come together, close together, they attract and annihilate. But for scroll rings, we were not, and of course, they had this critical distance which was not something which we expected. This was just one core length. This is something which we could not look at the repulsion with our scroll rings, but another group of Marcus Hauser in Magdeburg, they did work with straight filaments, 3-dimensional filaments, and they did see that there is a repulsive zone indeed. So, then we thought, why not look at a network of such rotors and how do they behave in the vicinity of each other. So, we considered them as point particles and we were thinking about chimera. So, this is something, anybody read Of course, all of you know Chimera, but this is a new thing. This is Hasjaru. That was Bengali literature people will know. It's a similar concept. Of course, when I looked at experiments with Chimera, these two are the first experimental evidences of Chimera. Both came out in the same time in the same journal, and one was by Ken Showalter with a network of chemical oscillators, another by Raju Roy and co-workers with laser systems. And then we thought we cannot work with so many spirals, right, at the time. It's very difficult to set up these experiments. So what would be the minimum that we need? So the minimal again has two ideas. One could be the 3 oscillators, 3 individual oscillators, 2 in sync, 1 out of sync. Would that be called a chimera? But again, there were other groups of Professor Roy and co-workers who said the minimum we need for a doublet, means 2 synchronized and 2 asynchronized would tell you no, it's a chimera. So we thought to go with this. The geometry would be more regular square, and of course to begin with we got the idea of pinning our, though we did pinning studies, I got the idea of pinning our scrolls, our spirals from the work of Professor Purit Paramananda, as was already described very nicely by this by the postdoc. I forgot her name. So she talked about these camphor rotors. So that is where I thought about rotors of spiral waves, and I wanted to see if spiral chimeras existed, and I knew that they existed in literature, but they were different from what we were looking at. So this was the chemical spiral chimeras, and each cell is an oscillator, and that gave the form of spiral chimeras. Edgar Knobloch, he talked about these two, but what we were looking at is spirals as rotors. So let us come to that. So we had 4 rotors in the vertices of a square, and we will now look at their, so they are identical heterogeneities. So the frequencies are fixed. So we look at their phase movement. So what do they happen to the phases? So we begin with 1, 2 and 3, 4 here we can see initially this is experimental results, they look like that, and when after about 3 hours, or actually they stabilize before that, but we have shown the data after 3 hours, you can see that 1 and 3 have synchronized. So these are results which we have color coordinated. So 1, 3 coordinates and 2 and 4 are out of sync. So this could be said to be like a chimera-like behavior, and the phase diagram also shows the same, but as you can see the rest are also, the phase are different. So it's basically phase oscillators in that sense, and we have also tried, now what we try here, what we change here is change the size of the square, the length of one side of the square, and we end up with cluster-like states. 3 oscillators going in exactly the same phase and 1 is out of phase. So these 3 are together and this one is rotating in its own time. So these are, we also moved to a network of 8 rotors, putting it in the vertices of an octagon, and then we saw that 3 of them moved in the same frequency. It's difficult to understand from here. So this 3, these 2 move with the same phase and the other 3 are out of phase with this. I'm out of time, okay. So we did simulations with the Barclay model and managed to find some, but then we thought why not go to the Kuramoto type of thing. We looked at the angle, phase angle and the frequency, and here we use the interaction energy as the difference of 2 Yukawa potential. So this is something that is taken as when we look at interactions of rotors and spiral and scroll waves. So this gave us very nice results of doublet, singlet, singlet, triplet, singlet, and also drifting phases, and we got a phase diagram here. So this is something interesting. We saw that drifting phases, they enveloped DSS chimera-like states, and within them was a triplet singlet state. So basically we want to see that kind of synchronization. We have very initial results in 3D, whether the critical distance has something to do with this distance of synchronization, and if heterogeneity can bring in some new things, more synchrony. Many thanks, and all thanks to the people who did the experiments, which are really difficult. Rishikesh, who has submitted his thesis, and Parvez, who is here, also posted, showed a poster yesterday. And I would like to thank DST and of course the organizers of PNLD for giving me this opportunity to speak. Thank you.
Thank you, Sumana, for wonderful talk. I enjoyed a lot. So is there any question? Otherwise, I have a lot of, yes.
Hi, Sumana. I have very stupendous experiments. So I was just wondering, this example that you showed of 2 pin spirals with different, pinning centers such that they have different frequencies. So I was like thinking theoretically, I could actually take one of them to be, like a source, and then essentially I can think that the higher frequency is basically acting to overdrive the slower frequency. So can't I understand the synchronization as simply the higher frequency one overdriving the
This is kind of like forcing, yes. In this case, it was more like forcing when one is big and one is small. If one is, sorry. When one is faster, it will actually take over the other frequencies, yes. That is true in the case of synchronization when they are different. But when we have mixture or they are all the same, then it becomes more interesting. Yes.
Yeah, and so one of my doctoral students actually was working on, what happens if you actually have these two spiral sources, but one is pinned and the other is at a particular angle.
Okay.
And so basically, like, is there a rotational symmetry? And she found that actually there is no rotational symmetry. There are certain angles at which it will annihilate the spiral, others in which both will coexist, others in which they will merge, and so on. So I was just wondering whether you have seen such phenomenology in your experiments.
No, I didn't. But we did try some with basically co-rotating spirals, which we are trying, because co-rotating spirals both being the same charge, they will never annihilate each other. They can just come close enough. But again, if you start, I think that is similar to what you said, if they start with different initial phases, though when we start experiments, we cannot really say what the phase angle, but sometimes it happens that they do not annihilate, but they try to both move together in this phase. That is possible, yes. That is possible. I think it's similar, right? Yes.
Right. Yeah.
Hi, so this is a very naive question, but this relates to the scroll waves that you observed. How exactly did you do that in your setup, given that you were looking at only the planar?
So we generally don't have a tomographic setup right now, and even if we do, it's really difficult to see more than one scroll waves. So we look at the scroll from the top. So it is like you see a ring, okay, the ring structure that is visible. You cannot really see the 3-dimensional what is happening to the waves that are going away. So you can see the ring from the top. So they are scroll rings that are basically horizontally placed.
Okay, so in that case, how do you look at the filament dynamics and how the filaments interact with each other?
So when we keep two rings close to each other, not only two, many rings close to each other, if they are in the same plane. So that's something we choose a recipe where they do not move in the horizontal. So if you remember, there is an alpha k plus beta n, right? They move in the normal direction as well as the binormal. We arrest their binormal movement and only look at the movement in the normal direction.
Okay, thank you.
Thank you.
So I have one very basic question. So chimera you define when you have frequency desynchronization as well. Right now, as I could see, the frequency was same for all the oscillators.
Yes. So we should call it rather chimera-like in cluster probably. Maybe, yeah, because without pinning it's not possible. Maybe with heterogeneities we have found some, but I don't know. Yes.
Thanks.
Yes? The phase is only the phase asynchrony, yes.
So this is accepted that frequency difference is not necessary condition.
Yes.
Only if you have only identical frequency, if you have a phase lag, this is also considered.
And also like in chimera, in general, it's very sensitive to initial condition. So in experiments,
yes, it is very difficult. It is very difficult. So what we are not really sure. We have not been able to get the phase diagram in our experience because it's really difficult to start this experiment.
How did you set the
how do we set? Yes, that Professor Rajesh Shinoy knows that very well. We were starting with, actually we always used to use spherical beads for our experiment. But then in previous pinning experiments where we did pinning and unpinning of such waves, but we found that the same kind of things was giving us different results and we were not sure why. And then suddenly one morning I realized that if it's a sphere and we are saying about a 2D system, right, in a sphere has different kinds of radius, right. I am having a thin layer of gel which is 2 or 3 millimeters and I have a sphere sitting on it which is say 3 or 4 millimeters in size, and a sphere has different radii in its different levels. So that's why we were not actually having the exact, so that's why we moved to now your cylinders. So cylinder from top to bottom has exactly the same radius. So that really took us a long time, and then Parvez redid all the experiments. So we put it specifically on the sides of a square. It is very difficult. You have to ask him how he did.
Last, again, fundamental question. Like chimera is symmetry breaking in a symmetric system. But when you pin the system, already symmetry is broken somehow.
No, this is actually you're ensuring that they are remaining in the exact same place, and they will keep on rotating like that.
So symmetry broken. So pinning is not like in theoretical model when we do pinning, so that somehow breaks the symmetry.
No, here you are basically keeping it, so it's like anchoring. And
so you
it
have
keeps
spontaneous
on rotating.
symmetry breaking in the system, which is completely symmetric system.
Yeah, it is not that.
Very good, fantastic. Okay, so if we don't have any questions, so let us thank Sumana and all the speakers, and thank you all of you for joining us.